All right, so now we move on to lesson 5.3, which is radical equations. Now, when we shift from radical expressions, which was 5.1 and 5.2, into lesson 5.3, what we're now going to be dealing with is instead of just taking radicals and then simplifying their form and making them either mixed or entire or adding and subtracting radicals, when we talk about radical equations, it's important to understand that we're going to be solving for specific x values that satisfy a given equation. Now, the steps that are involved in solving radical equations are the following. First of all, we want to state the domain or the restrictions for x, because in most cases, we need to make sure that the radical is actually going to produce a real number. Otherwise, we're going to be in the complex field, and we don't want that. The next step is going to be to isolate the radical on the one side, square both sides so that we can get rid of the radical, then solve for the variable, and make sure to verify your solution, which just basically means plug that x value back in, see if it's equal. All right, so let's go to example one where we're going to state the domain of the variable and solve each equation, aka we're going to repeat all the steps above. Now, what I'm going to do is I'm going to make this into 3 repeatable steps. So I'm going to take these steps above and just truncate them all together in 3 steps that we can follow for every single radical equation. Starting off with the first one, we want to figure out what our restriction is. To state our restriction, we're going to go part 1, and we're going to state whatever is under the radicand position, or whatever is the radicand, I should say, in this case just x, we set this greater than or equal to 0 because we want it such that we don't have x be a negative number. Now, if x is not a negative number and it's greater than 0, in this situation, the restriction is just simply that it's greater than 0. Now what we can do is we can go to step number 2. We're going to take that expression or that equation and rewrite it. Now I'm going to divide both sides by 3 because I want to isolate the radical on the one side. This is going to give me that the square root of x is equal to 5 over 3. And now from here, we're just going to take both sides and square them. And if I square both sides, I'm going to end up getting that x is equal to 25 divided by 3. Perfect. Okay, so now we have an x value, but before we actually say this is the complete x value and that this works, we need to make sure we verify it. So part number 3, here's where we verify it in both sides of the equation. We're going to write it as 3 square root of the x value, which is 25 over 9. Sorry, this should be a 9 here. Let's make sure that's correct. There we go, which is equal to 5 on the other side. Well, if I take this, this is the same as saying square root of 25, which is 5, times or divided by this square root of 9, which is 3. I can plug 5 over 3 in instead. I'm going to end up getting that my 3's cancel because 3 divided by 3 eliminates, and therefore I get 5 equals 5. Now, a statement we would often put here is off on the side or even right below it, we would say left-hand side equals right-hand side. This is a very common thing to express right at the very end, just to say that, hey, my 2 sides are equal to each other. Now, if we have more room, obviously we'll put this right below, but in this case, we're good. And if we figure out that we verified that this is the solution, I just want to make sure that you highlight your solution at the end here and say that this x is what will satisfy this radical equation. Okay, let's go over to part B. Now, part B has 4 equals the cube root of 8x. Anytime we see a cube root or a fifth root, any sort of odd root in terms of the index, what we're going to assume is that x can be an element of the reals because it doesn't matter if it's positive or negative. There is no restriction on x because there's no such x that I could plug under this radical that would make it a non-real number. So what I'm going to do is just say XER, meaning infinite solutions for x. Now what I'm going to do is state the equation again. 4 is equal to the cube root of 8x. I'm then going to take the third power or raise everything to the third power in order to eliminate the cube root. 4 raised to the power of 3 is 64. 64 is equal to 8x. I'm then going to divide both sides by the 8 to get rid of the 8 here. And therefore, this is going to end up giving me that x is equal to 8. Okay, now, again, once we figure out this x value, we don't want to just highlight it right away. What we're going to have to do is make sure that we verify it in both sides of the equation. So I'm going to write 4 is equal to the cube root of 8 times 8 within the radicand position. Now, this means 4 is equal to the cube root of 64, which, yes, 4 does equal 4 because the cube root of 64 is actually 4. And we can state that our left-hand side is equal to our right-hand side. And then as soon as you've proved this, go back to your value and make sure you highlight or box it. So verifying or checking your solution is very, very important because you never know. We might get an extraneous solution that we have to eliminate. All right, let's amplify the difficulty just a little bit. Now, I'm going to give you an equation that looks like the following. Again, our first step is always to state what is the restriction on x? The restriction comes from our Radicand position because we need a radical that will be greater than or equal to 0. So I'm going to state that 2x minus 3 must be greater than or equal to 0. I'm going to add the 3 across, so let's go plus 3 and plus 3. This is going to give me 2x is greater than or equal to positive 3. My last step to state my overall x restriction is going to be divide by 2, and I figure out that x is greater than or equal to 3 over 2. So as long as we have an expression where x is greater than or equal to 3 over 2, we're like, okay, perfect, this works. Now what we're going to do is we're going to start solving the equation. So often what I do at this point is I just restate out the original equation. So square root of 2x minus 3 is equal to 12. Now we want to get the radical on its own. So I'm going to subtract 3 from both sides. This is going to end up giving me that the square root of 2x minus 3 is equal to 12 minus 3, which is 9. In order to isolate the position or the Radicand position and get rid of the radical, I'm going to square both sides. When I square both sides, this ends up giving me that 2x minus 3 is equal to 81, because 9 squared is 81. And then from here, what I'm going to do is add the 3 across. So plus 3 and plus 3. This is going to then give me 2x is equal to 84. My very final step is to divide both sides by the 2. And when I divide both sides by 2, I end up getting that x is equal to 42. Awesome. Now, we just need to quickly verify that this is actually the solution. So to verify this, let's do this off to the side. And just as a way to create space for our other problem here, what I'm going to do is I'm just going to loop all of this and then just shift it over slightly, just so that if we require some more space on the right, we can use it here. So there we go. We'll push it to there. And then I'll do my verification step just right off to the side here. So for step number 3, we're going to rewrite that original equation again, but we're going to sub in the value. So it's going to be 3 plus the square root of 2 times the x value, which is 42, minus the 3 that was underneath. And then supposedly this is equal to 12 on the right-hand side. This means 3 plus, well, 2 times 42 is 84. 84 minus 3 is the square root of 81, which is supposedly equal to 12. This is 3 plus 9 equals 12. And therefore, we get 12 equals 12. Left-hand side is equal to the right-hand side. Nice. So we've got a verification where our 42 works. And so we want to go back and highlight that. And as long as we've stated our restriction, we've done our verification, and we've properly solved this, we now have a value. All right. Now, just as a way to kind of make sure that I have enough space here, because I think this might run into our next problem here. We'll try our best to work around it here. Let's say we go over to this problem here. Now, what we want to do is for step number 1, we're going to state our restriction. So step number 1, we take the x plus 1, which is greater than or equal to 0. We then subtract 1 from both sides, minus 1, minus 1. This ends up giving us that x is greater than or equal to negative 1. So now that we've stated our restriction, that gets one step out of the way. And maybe I'll just move this over just so it doesn't run into the next line here. Now what we're going to do is for step number 2, we're going to state the equation again. This is 4 square root of x plus 1, which is minus 5 is equal to 3. From here, let's start by adding 5 to both sides. I think that's going to be our best step because we want to isolate this radical. I get 4 square root of x plus 1 is equal to 8 on the other side. Now, if you have a coefficient term and you can divide it, I highly recommend you do. So in this situation, what I'm going to do is end up dividing both sides by the 4. When I divide both sides by 4, it eliminates it from the left-hand side, and I have the square root of x plus 1 is equal to 8 divided by 4, which is 2. Now I'm going to square both sides in order to get rid of the radical, or to get rid of the square root. This gives me x plus 1 is equal to 4. And if I subtract 1 from both sides, I'm going to end up getting that x is equal to positive 3. All right, now, just as we've done before, we want to make sure we verify that this is the correct solution. So we're going to plug it into the original. For the sake of space here, let's see if I can condense this. I might have to do a bit of rearranging here. So let's say I'm going to move all of this up and right next to here. That should give us enough space here. So if I put it right here, there we go. And then I'm just going to shift all of this stuff over a little bit and just create some room on the right-hand side. There we go. and then I can do my verification just off to the side here. So for step number 3, we're going to verify it, and we're going to go, okay, let's make sure we plug this in here. So this is going to be 4 square root of, we plug in the value of 3 plus 1, minus 5 on the outside is supposedly equal to 3. We take this and we go, well, 4 square root of 4 minus 5 is equal to 3. We end up getting that 4 times the square root of 4, that's 4 times 2 is 8. 8 minus 5 is equal to 3. Therefore, 3 equals 3. And our left-hand side is equal to our right-hand side. And we're happy with this. As soon as we get that, we're like, highlight our value, meaning that this is the appropriate solution, and we're set. All right, let's go into some more problems on the next page here. So suppose that we were given these problems here. Well, on surface value, you might be like, this might be a little complex. Now we have 2 radicals. But what we want to be thinking about is, if you see that they're both the same index and same radicals, so they're both to the 2, they both have x in the radicand position, let's see if we can combine the coefficients. What I'm going to do is, first of all, we want to state our restrictions. So x must be greater than or equal to 0, because we can't have a negative radical here. Once we state this, we can go into our problem solving and say, well, if I take the 3 times the square root of x minus 4 is equal to the 2 square root of x plus 1, what I'm going to do is I'm going to start by isolating for the radical by taking this 2x, or 2 square root of x, moving it over to the other side, and at the exact same time, I'm going to move the 4 over from the left to the right. Now, by doing this, what this allows me to do is take 3 square root of x minus 2 square root of x is 1 square root x, which is equal to, on the other side, 1 plus 4, which is 5. Now I can take both sides, raise them to the power of 2 in order to get rid of the radical, and this gives me x is equal to 25. Now, to verify in step number 3, we just plug it back into the original. 3 square root of 25, and then let's just make sure I got it all right here, minus 4 is equal to 2 square root 25, and then plus 1. Well, this is the same as going 3 times 5, which is 15, minus 4, which is equal to 2 times 5, which is 10, plus 1. And what we get is that 11 equals 11. Left-hand side is equal to right-hand side. And we're satisfied with this. We're like, hey, it works. We verified it. It's all good. Perfect. Okay. One more example for this section here. So what if we go to here? Well, we always want to start with our restriction. So we're going to go for step number 1 here. I'm going to write this as 2x minus 1 must be greater than or equal to 0. Because again, we want our radical to be such that it's not a negative number, so that it's not an imaginary. Now from here, I'm going to add 1 to both sides. So plus 1 plus 1. This gives me 2x is greater than or equal to 1. And then if I divide both sides by 2 in order to get my restriction, I get that x is greater than or equal to 1 over 2. Now we're going to continue our problem solving here. So step number 2, we go to actually solving the equation. The square root of 2x minus 1 and then plus 5 is equal to 2. Of course, what we want to do is isolate our radical first. So we're going to subtract 5 from both sides. And this gives us that the square root of 2x minus 1 is equal to negative 3. I'm going to square both sides. Let's move that up as much as we can. So we square both sides. And I want to make sure it's surrounded everything on both sides. So square and square. This is going to give me 2x minus 1 is equal to positive 9. Because if we take a negative and raise it to an even power, it becomes positive. I'm going to add 1 to both sides at this point. When I add 1 to both sides, I get 2x is equal to 10. I divide both sides by 2. And therefore, I get that the x value is equal to 5. Perfect. Okay, so now we have an x value. Let's make sure we verify it to show that it works. So just off to the side here, maybe I'll do up here somewhere, just right at the top. Step number 3, I'm going to write this as the square root of 2 times 5. There we go, plus 1, minus 1, sorry, make sure I get this right. Plus 5 is equal to 2. There we go. We take the square root of 2 times 5 is 10, minus 1 is 9. So I'm just going to write it as square root of 9. Plus 5 equals 2. And then that means that 3 plus 5 equals 2, or 8 equals 2. And immediately you should be like, wait a minute, this isn't true. This is not equal, not equal, not equal. All of these are not equal because obviously when we take 2 and we compare it to 8, those are not the same value. So what does this mean about our solution? This is the first time we're now seeing where this is an extraneous root. If this ever happens, what I want you to do is circle your value, put a line through it, and immediately write ext. So just like we did with previous units, when we went to verify solutions, we would always make sure they work. If they didn't work, we had to cross them out and say extraneous, or that they didn't apply to the problem. In quad equations and quad functions, we saw this quite a bit when we said, hey, which of these things don't apply to the application problems? And we couldn't have things like negative time or negative distance. So therefore, we looked at this and we said, hey, those values are extraneous. Now we have a way of saying in this unit, we can also determine extraneous roots. Okay, now that leads us into the bubble below. In this last example, we may have situations which the domain, it maybe doesn't work with the domain, but other situations, it just doesn't work with the overall verification of the system. So these solutions in which we get these no solutions are considered to be extraneous roots here. Or when both sides of the equation are not equal to each other, we consider this to be extraneous. All right, let's go into example 2, where we're just going to continue this type of overall mathematical approach where we state our restrictions, we solve, and then we verify our solution. Let's say we're given this one here. Well, right away, what we want to do is state the restriction. So I'm going to go part number 1. We're going to write 2 minus m must be greater than or equal to 0. If I add m to the other side, I'm going to end up getting, so let's just put plus m and plus m just to make it positive. I get 2 is greater than or equal to m, or you can think about it as m is less than or equal to 2. So as long as m is less than or equal to 2, we're like, okay, that satisfies us for this. Now we're going to go to part 2, and we're going to do the algebra around here. We have m is equal to the square root of 2 minus m. Now, if I square both sides here, so I go squared and squared, this ends up giving us that m squared is equal to 2 minus m. From here, we're going to recognize that if we have an m squared and an m, we can't eliminate the m's. What we have to do is we have to build out a quadratic equation. I'm going to take all of the stuff over here and subtract and add it as a way to bring it over to the left-hand side here. This is then going to give me the following. I'm going to get m squared plus m minus 2 is equal to 0. And now we have a quadratic. So what we can do is we can factor this. What multiplies to make negative 2 adds to make 1 in the middle here. The values that work for this are going to be the following. We're going to get m plus 2 and m minus 1 is equal to 0. And therefore, the two possible solutions for this are going to be m being equal to negative 2 or m being equal to positive 1. So those are our options for the m values, because remember, they're always opposite of whatever you see in the brackets from our quadratic equations unit. Now, let's verify and see which solution works, or if both of them work, or if none of them work, we got to make sure. So I'm going to go back to the original and be like, let's start off with negative 2. Negative 2 is equal to the square root of 2 minus the negative 2. Well, this is saying negative 2 is equal to the square root of positive 4. And the square root of positive 4, this means that this is negative 2 equals 2. This clearly is not equal to each other. Therefore, when we go down to our solution, I want you to circle the m equals negative 2, put a line through it, and then just make sure you write ext or extraneous. Okay, now let's check about m being equal to 1, because who knows, maybe that solution doesn't work either. 1 is equal to the square root of 2 minus 1. Well, this is 1 is equal to the square root of 1. 1 definitely does equal 1. Therefore, left-hand side equals right-hand side. And if we have this situation where left-hand side equals right-hand side, you can go down to your m's and then highlight the m being equal to 1. That works for us here. Perfect. Okay, let's try B using the same idea here. So in B, we have where we have it in terms of n now. We're going to state our restrictions. So our restriction will be that 5 minus n must be greater than or equal to 0. If I add n across to both sides, this ends up giving me that 5 is greater than or equal to n. Or you could always read that as n is less than 5. So if you prefer to see it this way, n is less than or equal to 5, that means the exact same thing here. Now what we're going to do is from here, we're going to actually solve for the n values. So we have n minus the square root of 5 minus n is equal to negative 7. From here, what I need to do is I'm going to just do a simple swap here. Whoops, sorry to have the page moving there. I'm going to do a swap. If I know that this is a negative radical and this is a negative term, let's just swap their positions here. So what I'm going to rewrite this as is n plus 7 is equal to the square root of 5 minus n. And the reason I did this is just so that everything is positive, and more importantly, my radical is positive. Now that my radical is positive, I can take both sides and square them. So squared and squared. Perfect. Let's just make that a little bit better. Perfect. Now, here's where you don't want to get caught in the trap, is when you take n plus 7 and you square it, it's taking the same binomial and writing it out twice. So I'm going to write this as n plus 7 and n plus 7, because I don't want to just square them individually, is equal to 5 minus n, because we've undone our square root. Now when I expand this, this gives me n squared plus 14 n plus 49 is equal to 5 minus n. I'm going to take those terms from the right-hand side and move them over. So minus 5 and plus n, minus 5 and plus n over here. And I'll just write them below the sequential terms here. There we go. Then this gives me where I have n squared plus 15n. And then plus, if I have this, it should be 44, which is equal to 0. Now, what multiplies to make 44 and adds to 15? Well, those two numbers are going to be n plus 4 and n minus 11 is equal to 0. Therefore, the two terms that are working here are n minus 4 and n equals 11. There we go. And these should both be positive, I believe. So this needs to be positive as well, meaning this should be negative 11. Excellent. Okay, now from here, let's just double check and see which solutions work. So in our verification process, we're going to go for part number 3 here. I go below and I go, let's start off with maybe 11. Negative 11 minus the square root of, and we're plugging this back into the original, 5 minus negative 11, close the bracket, is equal to negative 7. This is negative 11 minus 5 minus 11 is the same as 16, which is equal to negative 7. And this gives us negative 11 minus 4, that's negative 15, is equal to negative 7. No, this is not true. As soon as we figure out that it's not true like this, go back up to your n equals 11, cross it out, and then write ext. Perfect. So extraneous, we want to make sure it's out of there. Now from here, we're going to then verify our second solution, negative 4 minus the square root of 5 minus, and I'm going to make sure that's a little neater, 5 minus negative 4, which is then equal to negative 7. This gives us negative 4 minus 5 minus 4 is the square root of 9, which is equal to negative 7. 4 minus the square root of 9, which is 3, gives us negative 7. And because we get negative 7 equals negative 7, therefore we say that the left-hand side equals the right-hand side. We're satisfied with this solution. We want to go back up and then highlight n equals negative 4 as a solution. Perfect. Okay. Now, we have one more example, which is C here. So let's make sure we do this one here. Off on this side here, what I'm going to do is I'm going to say, well, right away we want to state our restrictions. So for part number 1, we're going to write 2x plus 3 must be greater than or equal to 0, because we can't have a negative square root. There we go. I'm going to subtract 3 from both sides, so minus 3 and minus 3. This is going to give me 2x is greater than or equal to negative 3. When I divide both sides by 2, this ends up giving me that x must be greater than or equal to negative 3 over 2. Perfect. Okay. Now, what we're going to do is we're going to start solving. So let's see if we can fit this all below here. I have x and then minus the square root of 2x minus 3. And then just to make sure that's good, or 2x plus 3, I should say, is equal to 6. Now from here, what I'm going to do is I'm going to swap these. And just like we did in the previous one, if it's a negative radical here, I'm going to swap it and bring this term over to the other side. So let's rewrite this as x plus or x minus 6, because I'm bringing a positive over to the left-hand side, is equal to the square root of 2x plus 3, where the 6 and the root have changed places. Now what we're going to do is we're going to square both sides in order to get rid of the radical from the right-hand side. Now, again, with the binomial squared, we're going to write this as x minus 6 times x minus 6, which is equal to 2x plus 3. Now, unfortunately, we've kind of run out of space here, so we're going to continue it up on the right-hand side here. Actually, we have a little more space. We'll deal with it. So we have x squared minus 12x, and then plus 36, because 6 times 6 is equal to 2x plus 3. I'm going to bring these terms from the right-hand side over. When I bring them over, I get x squared minus 14x, and then 36 minus 3 is plus 33, is equal to 0. Now I can continue this part up on the right-hand side here. So the factors of this one, what multiplies to make 33 and adds to make negative 14, that would be negative 11 and negative 3. So when we go up here, we're going to say x minus 3, or x minus 11 even, I don't really care which order they're in. There we go, is equal to 0. Now this means my two solutions are either x equals 11 or x equals positive 3. Now from here, we just need to verify and see which ones work. So for part number 3, I go down here and I'm like, well, the original tells me that it's 11 minus the square root of 2 times 11 plus 3 is supposedly equal to 6. There we go. And I want to make sure it's all included under the radical if it needs to be. That means we have 11 minus 2 times 11 is 22. 22 plus 3 is 25. Square root of 25 is 5. So this is equal to 6. 11 is equal to, or not 11, 11 minus 5, which is equal to 6, equals 6. Therefore, left-hand side equals right-hand side, and we're satisfied for that first value. For the second one, we want to plug it in as 3 minus the square root of 2 times 3 plus 3, which is equal to 6, supposedly, on our right-hand side. If we do this, it's 3 minus 2 times 3 is 6, plus 3 is 9. 9 square rooted is 3, which is equal to 6. 0 definitely does not equal 6. And because it's not equal, now we're going to go up to our 3 as our value, circle it, put a line through it, and write ext. There we go. And then we want to make sure we highlight our x equals 11 as the solution because it did end up working. So we're satisfied with that. Okay, let's go to our next page here. Now we're going to go to the more application style problems. So in this situation, what they give us is they say we have some sort of period that is representative of a pendulum swinging backwards and forwards. Now, just to help visualize this, because a lot of you, or some of you might not take physics 20, I shouldn't say a lot of you, some of you will, we want to just draw out a simple pendulum here. So off on the side, I'm just going to draw some sort of pendulum with a bob on the end, meaning like some sort of mass, and it's swinging backwards and forwards about some middle line here. So I'm just going to draw like a dotted version of the line over here, indicating that it rocks back and forwards between these two. And I'm going to show an arrow going from the left-hand side to the right, and then the right going to the left. That represents one period or one cycle or one rotation. So I'm going to say period is equal to one cycle / rotation. And this is just because when we deal with this, that red line is that kind of middle line. It's its resting position. And one period is when it goes all the way to one side and all the way back. That's considered to be one complete rotation or cycle. Now, in this, they give us a formula that would appear in the Physics 20 formula sheet, which is, if we want to determine period, we can say it's 2 pi times the length, or times the square root of the length of the string over gravity, because 9.81 represents the acceleration due to gravity. Now, they tell us that the p-value is 2 seconds because the period is 2 seconds. To go there and back takes 2 seconds. So I'm going to write p equals 2 seconds. Now that we know that our period is 2 seconds, we know what this is, let's plug it in and figure it out. First and foremost, we need to establish our restriction. Our L must be greater than or equal to 0 because we're not going to have a length of a pendulum that's negative. That wouldn't make sense. Now from here, once we've stated our restriction, we can actually solve this. Period, which is 2, is equal to 2 pi times the square root of the length of the string over the 9.8, which is the gravity. In order to start isolating this, I'm going to divide both sides by 2 pi. There we go. 2 divided by 2 is just 1 over pi, which is equal to the square root of L over 9.8. Now from here, I'm going to take the square of both sides because I want to eliminate that radical. So there's my square, there's my square. This is going to give me 1 squared is 1 over pi squared, which is pi squared, is equal to L over 9.8. Now from here, I'm just going to multiply both sides by 9.8 because if I can multiply both sides by 9.8, I'm going to eliminate the 9.8 on the right-hand side and move it over. Therefore, this gives me that the length of the pendulum is equal to 9.8 divided by pi squared, which means that the length of the string to the nearest, let's say, what did they want it to? The nearest hundredth of a meter? We want 2 decimal places. It's 0.99 meters. So basically a meter, very, very close to it, but almost a meter. There we go. Now, we could always verify this, right? So if we really wanted to, we could plug this into the original radical, see if it satisfies both equations, that 2 equals this radical times 2 pi, and verify the solution. But I'm okay with this for now. I think this is okay. Okay. Now, one thing I might just add to this is when we multiply by the 9.8, I might just put brackets around everything just to show that we're multiplying both sides by this 9.8. And then I'll just clean up this side here just to make sure that's a little bit better. Perfect. Okay, now last example, we consider a parallelogram. Now, if you don't know what a parallelogram is, this is a shape that looks like the following. Here's the 2 sides for the one piece. Here is the 2 sides that are from the other piece. And with these, I know I represented these as some gaps, or I have some gaps. Maybe I'll make sure that these are exact. So let's say I draw my 2 sides here. So here and then here. And then I draw my tops here and here. There we go. That's a little bit better. Our 2 sides here are the same. So I'm going to put a dash. I'm going to put a double dash for the other 2 sides that are the same. Parallelograms are where we have parallel sides that it's almost like a rectangle, but like a little bit pushed over. Now, they give us 2 sides for this. The first says that we have a side length that is the square root of 14n minus 45. So I'm going to write that down here. Let's say that this side here is our square root of 14n minus 45. And that's for both of these here because it is a parallelogram. They share the same value. 14n minus 45. Our other ones are going to be 2n. So 2n and 2n. Now, if these are both 2n because they're parallel, and then we have 14n minus 45, which are the same length and they're parallel, they told us that the perimeter of this is 54. So determine the actual lengths of this, we need to solve for the n value. So to do this, what we're going to do is we're going to set up our equation here. Off on the side, we're going to write it as for part number 1 here. Well, maybe we should actually state our restriction just in case, because you never know. I think it might be important just to determine the value from here. So maybe I'll do the restriction over here down below the shape. I'll write it that the 14n minus 45 must be greater than or equal to 0 because we don't want to have a negative length or a negative radical. Now from here, when I isolate this, I'm going to go 14n is greater than or equal to positive 45. If I divide both sides by the 14, 45 divided by 14 unfortunately doesn't give us a nice value, but it gives us an n that must be greater than or equal to 3.21. Okay, so as long as our n is greater than 3.21, we're satisfied here. Now, from this, we're going to go back up to the right-hand side here, and we're going to start solving this. So for step number 2, I'm going to say, well, the perimeter of any shape is always the outsides all added together, or the outside lengths added together. They told us the perimeter was 54. Our length in this case is the square root of 14n. I almost forget to put the 1 every time there. 45 times, or plus 2 times the 2n, which is our other 2 lengths. Now when I expand this out, I get 54, which is equal to 2 times the square root of 14n minus 45, then plus 4n here. Now what I want to do is, if I realize that these things can all be divided by 2, I say we just divide them all by 2 right away, because if there's a factor we can reduce it by, this may help us in the long run. So if I divide all these sides by 2, I get 27 is equal to the square root of 14n minus 45, and then plus 2n here, because we've divided them all by 2 now. Now I'm going to isolate the radical by subtracting away 2n from both sides. This is going to end up giving me that I have 27 minus 2n is equal to the square root of 14n minus 45. I got to make sure I square both sides in order to undo the radical. There we go. And then doing the math here, 27 times 27, because we would write this out twice. So maybe I'll just, to save some room, I won't write it out twice. I'm going to get that this is 729. And then our middle term is going to be negative 108n. And then we're going to go plus 4n squared is equal to 14n minus 45, because we got to eliminate that radical. I'm going to bring over all the terms to one side. In particular, because the 4n squared or the n squared term is positive here, let's bring over all of these. So I'm going to go minus 14n plus 45, which will bring it over to the left-hand side here. This will give me 4n squared. My second middle term will be negative 122n. Let's just get rid of that there. And then this is plus 774, which is equal to 0. And the nice thing is, at this point, we can also reduce this by a factor. So I'm going to reduce these all by 2. I would like to do 4, but if it's not available, 2 will do. Now, this is going to give us a quadratic equal to, let's see what space we have here. Maybe let's do it off over here. We'll continue somewhere below here. So we're going to write this as the quadratic we get is, and actually no, let's do it like pretty close to here. It's going to be 2n squared, and then our second middle term is going to be negative 61n. 774 divided by 2 is plus 387, and this is all equal to 0. Now what we're going to do is we're going to put this into quadratic formula where a is equal to 2, b is equal to negative 61, and c is equal to 387. If you see these really big values like this, I would highly recommend you just do quad formula, just because the factors are not going to be nice, and you can't really do a factor by inspection when the value of a is greater. So let's write that there. There we go. Okay, now plugging this into quadratic formula, we're going to get that x is equal to minus the negative 61, which is the b value, plus the square root of, and let's make sure that's pretty long here. This is going to be negative 61 all squared, minus 4 times the a value, which was 2, times the c value, which is 387. And then this is going to be all divided by 2 times 2, which is the a value. Perfect. The two x values you get out of this when you calculate the plus and minus version are either x equals 9 or x is equal to 21.5. Okay, now from here, we actually need to calculate what the specific lengths are, because that was just the n value, right? And so I shouldn't even be really calling it x as more as I should be calling it the n values from here. And let's actually just fix that here, because if we're solving for n roots, I'm going to make this n here at the original. I'm going to make this n and then this n. If we're solving for all the n's, now to finish up the solution, we just need to plug these into those radicals above that are on the shape, or plug it in for n on the lengths and widths here, and then be like, what is it actually equal to? And we're going to do that for both the numbers here. So in the limited space I have below here, what I'm going to do is try to complete that here. So I'm going to say, therefore, we're going to take the 2n, which is equal to 2 times 9, which was our first n value, which gives us 18 centimeters as the one width. Then, if we want to figure out the length that goes with that, we're going to do the square root of 14 times the 9 minus the 45. And this ends up giving us that we get 9 centimeters for the length. Awesome. So we have a length and a width according to that. Now what I'm going to do is do the exact same thing, but instead I'm going to sub in the 21.5. So times 21.5, I get that I have a length of 43, or a width of 43, I should say. And then for the square root value, I'm going to get that I have 14 times the 21.5 bracket minus 45. And this should all be under the radical, so I'm going to make sure it's there. This will be equal to 16 centimeters. There we go. So these are the actual values for the length and width given those certain values for n that work in this. Okay, and again, neither one are extraneous because both n values are greater than or equal to 3.21. So as long as we have that, we're satisfied with this. And then just to provide a little bit of direction on here, I'm just going to do an arrow here. So I'm going to be like, we went from here to then into the quadratic equation here, just so that you can see that step. Perfect. Okay, here's where you're going to want to go into your assignment and try some of the textbook questions. I've also probably given you an additional handout that I would like you to go through that goes through equations. So either one. And then what I'd recommend is go to the textbook if you're looking for specific application problems, because that's where you'll see problems like these or even the pendulum questions. All right, good luck with your practice.